Okay, so we're going to play around with r equals the sine of 2 theta, and I started collecting some polar points, and I can't figure out how my mic is. Okay, so the graph paper I gave you today, I don't know if anyone noticed, it has 10 rings instead of 8, which I like better because like decimals based on 10. All right, so I'm going to try to graph in blue here. So I get the point 0, 0. I get the point pi over 6, square root of 3 over 2. And square root of 3 over 2 is what, like 0.87-ish? Somebody help me on a calculator. Square root of 3 over 2. 0.86? Okay. So that's going to be, so let's see, that's 9. This is 8. Yeah, it's going to be right about here. I have 10 lines this time. Yeah, so the graph paper I gave you today has 10 lines to use it like decimals. Yeah. Pi over 4, 1. So I'm going to make my outer ring 1. Square root of 3 over 2 goes, oh shit, I put that in the wrong spot. Pi over 4 is right here, 1. And then pi over 3, 0.86-ish is going to be around there. And then it comes back to 0. So it looks like it whips out, loops through those points, and then comes back. So there's one, so I've got one leaf from going to 0 to pi over 2. And if I keep tracing that, it says when I get to 2 pi over 3, and then keep in mind 2 pi over 3 is this angle right here, I have a negative radius, which means I have to go backwards through that angle. So I kind of missed that. And so that means the point 2 pi over 3 negative square root of 3 over 2 should be right about there. My next angle, 3 pi over 4, comes right through here. And the negative angle makes me head backwards through the pole, which is going to put me right there. 5 pi over 6, again, has a negative radius, so that puts me back through the pole right about here. So it looks like this thing comes looping around like this, and then it comes down to the 4th quadrant and loops around. Any idea which quadrant we're going to hit next? Based on that looping? No. 3rd quadrant, yeah. It jumped around to the adjacent quadrant before where it is. So this one is going to swing around and head through this quadrant here, hitting these points. So it's going to loop around here like that. And then finally, we're going to get into this quadrant and go bing, bang, boom, and stop there. So it's going to loop up, around, and down. So this is the first leaf. This is the second leaf. This is the third leaf. And this is the 4th. And I always thought it was cool watching these things evolve to see what order the leaves appear in. Okay, so we got ourselves a little 4-leaf flower here, 4 petals. Now this point over here is the point pi over 4, oops, 1. And when I'm doing polar notation, I like to put a semicolon, not a comma. Just to remind myself that is a polar point, not a rectangular point. Oops. Excuse me online, I just bit an apple. So we want to find the tangent line through that point there. And that's when we have our fun parametric form for this. Questions on my graph there? Now, I've done this one before, so I didn't feel the need to pull out my calculator. But in general, I'm going to be graphing this on my calculator and try using the calculator to try and figure out how to get it on paper. You guys all good with calculator graphing? Zach's got the prettiest calculator of all here. Congratulations. Okay. Can you look at that and guess what the slope might be there? Looks like the slope's -1, huh? Yeah, so we're going to prove that with the crazy slope formula for polar. All right, so polar
Wait, what? It's actually -1?
slope formula. Yeah. So polar slope formula, slope is dy dx, not dr d theta. We talked about that last class. And here I'm going to use the fact that y can be written parametrically. And so what I really want is the derivative with respect to theta of y, which is r sine theta, over the derivative with respect to theta of x, which is really r cosine theta. So we're using the ideas from parametric equations to do polar. And so that gives us the slope formula, dr d theta times sine of theta plus r times cosine theta all over dr d theta cosine theta minus r sine theta. And we have to plug in what r and dr are. So in this case, r is what we started with, sine of 2 theta. What's the derivative of that? That's a theta. Dr d theta will be what then? Two cosine theta, 2 cosine 2 theta, right? All right, so we want to drop those guys in there and play in place of r and dr d theta, and then we want to evaluate that when theta is pi over 4. So next step, we're trying to find dy dx evaluated when theta is equal to pi over 4. So I'm going to try and do that all in one shot here. So that's going to give me 2 cosine of 2 times pi over 4, which is really pi over 2, times the sine of pi over 4, plus the sine of pi over 2 times the cosine of pi over 4, all over, let's see, did I get that right? I think so. Yeah, slope in polar is just a pain in the ass. But we're going to do it anyway. This is what we did yesterday with a different problem. And this one's actually easier than the problem yesterday, I think. So what do I want next? I want dr d theta, so that's 2 cosine pi over 2 times the cosine of pi over 4 minus the sine of pi over 2 times the sine of pi over 4. All right, and some stuff is going to zero out here. Let's see, cosine of pi over 2 is 0, right? So that means this stuff is 0. This stuff is 0. Sine of pi over 2 is 1. So up here I'm going to have a 1 times the square root of 2 over 2. Down here I'm going to have a minus 1 times the square root of 2 over 2. So do we have a rough idea what the slope's going to be now? Yeah, it looks like it's -1, which we were kind of predicting looking at our almost accurate graph. All right, how do we find the line in polar? So that's rectangular, y equals mx plus b. And we just showed that m is equal to -1. So, what's that? Yeah. So we're going to use that same parameterization. We did this the other day, I hope you remember, Jeff's blocking it out there, or he's texting his mom this. What are you doing? So y is really r sine theta, and r is really sine of 2 theta. Actually, do I want to do that here? No, we're not going to do that here. That is incorrect. On the other side, I'm going to have a -1, and I'm going to have x is really r cosine theta. And then I still don't know b. We could solve for b. So let's see, how would we solve for b? Well, we know the point we're going through is the point, let's see, r theta is going to be -1 semicolon pi over 4. Ooh, I wrote that backwards before. Points are usually stated r then theta. So we could plug in here. R is -1. Sine of pi over 4 is the square root of 2 over 2. And that's supposed to be equal to -1 times r is -1. Cosine of pi over 4 is the square root of 2 over 2. And so we can solve that for b. That means I have a positive square root of 2. I'm going to subtract it to the other side, which means I'll have negative square root of 2 over 2 minus square root of 2 over 2, which equals the square root of 2, or negative square root of 2. Okay, now I have b. So the okay, now that is the rectangular line. Remember we found the polar line the other day? Does anybody remember the formula for a polar line? It's r equals b divided by some crazy stuff. No, I don't have a song for that. Sine of theta minus m cosine theta. So the polar version of this line is going to be negative square root of 2 over the sine of theta minus -1 is going to be plus cosine of theta. So let's graph that and see if it actually looks polar to my, looks perpendicular, tangent to my curve. So you can use the TI. I prefer the Desmos calculator for these. Let's see if I can get to that here. So my original function is the sine of 2 theta. Oops, I got to write r equals. There's that cutie. We can zoom in on it a little bit. Oops. All right, and now we think if I graph r equals negative square root of 2 divided by the sine of theta plus the cosine of theta, I should get the tangent line. Oh shit, I got a sign error somewhere. You got the right line? Oh. Interesting. How did we get the wrong line? Oh, we do have a sign error.
Oh, that should be positive right there.
It should be plus. There it is. Okay, so where did we mess up? So the negative square root of 2 is wrong. We have the wrong y-intercept.
Oh.
And if you look back at my picture,
Why is that wrong?
well, take a look here.
No, not me.
Oh.
Not you.
Okay. Can you see, looking at this black line that I'm estimating as our tangent line, its y-intercept is going to be over here, which is a positive number, not a negative number. So we have a mistake somewhere. I'm not teaching it wrong, I'm just doing it wrong.
Well, it's just the last step.
R theta. Let's see. The slope is definitely -1. That looks all right. Oh, here's our calculation for the y-intercept. That's where the mistake must be. All right, so we've got... Oh, yeah, there is a mistake here. Oh, r isn't -1, it's +1. Why did I write r as -1? Maybe. Yeah, r is +1 at that point. +1, +1, +1, +1, positive, positive, positive. Yeah, and then I wrote this point backwards too. The point's supposed to be r theta, r semicolon theta. And so r is 1 there, theta is pi/4. So that is this point right there. Whew. Okay, we fixed it. Can you see the good point of using a graph to help do stuff? So one thing on those tests I gave back, there were some spots you guys could have checked stuff by graphing, and I made a note on some of your problems about that. There should be a plus. I didn't check the graph on yours anywhere? All right, I don't know. All right, next problem. We have to find the area. Can we do that? Was right, but I was wondering if you graphed it to check.
He did not like that I forgot the. I forgot it.
All right, so here comes the fun. What should alpha and beta be for our boundaries? We could go 0 to 2 pi. That would give us all 4 leaves. Because 0 to pi/2 gave us 1 leaf, pi/2 to pi gave us the second leaf, and so on. So the period of this sucker is definitely 2 pi. Or we could just find 1 leaf. We could integrate from 0 to pi/2 and multiply the whole thing by 4. Another way to do it too. So the question is, what would you rather plug in, pi/2 or 2 pi?
2 pi.
2 pi sounds easier to plug in, doesn't it? That's a good question. Will we get negative areas? Let's do it both ways and see what happens. Polar's a whole different world. Yeah. Like parametric is weird because we integrate backwards accidentally sometimes there. Remember we had a negative area when it should have been positive just because the curve was being traced in a negative direction. All right, so let's see. R is sine of 2 theta, so we want r squared. So then here, I'm going to try what Zach's, whoa. I'm going to try what Zach said. My pen sounds a little upset about that. And Zach said, let's integrate as theta goes from 0 to 2 pi. And that's going to be the sine squared of 2 theta. So I need some kind of identity to get rid of the square. Use the half angle formula. And so my recollection is the half angle formula that says the sine squared of x is equal to 1 minus the cosine of 2x all over 2. But we don't really have an x here. What do we have? 2 theta. So that means in my formula on the right, I'm really going to have 4 theta, 2 times 2 theta. Yeah. Okay. So 1/2 integral from 0 to 2 pi of 1 minus the cosine of 4 theta all over 2 d theta. And we break that up, get them done. So area going to equal that 1/2 out front. I'm going to have a theta plus 1/4 cosine 4 theta. No, it's still minus. Wait, all over 2. Did I mess that up? Let's go back and look. Let's see, I'm taking cosine goes to sine. Oops. Yeah, it stays negative. What? Talking to me? Well, I have 2 different halves. I have this half here, and I have this half in there. I didn't pull anything out, except for the original half. Okay, so it's going to give me 1/2 times 2 pi minus, let's see, sine of 8 theta is 0, correct. All over 2 minus 0 minus 0 all over 2. So it looks like I get pi over 2 for the final area. Is that reasonable? Let's see. There's a circle. Inside that circle, I have this cute little leafy thing. Looks like that. My circle has radius what? Radius 1, because that's as far as the leaf went out, right? So the area of this circle is pi r squared, or just pi. So according to this, my leafy thing takes up half of the inside of a circle that circumscribes it. No, the whole, this is all 4 leaves, right? Because Zach said, let's go from 0 to 2 pi. Let's do all 4 leaves at once. So it turns out, even though it's looping around there, the integral still seems to be okay with not screwing up with negatives, which is weird. It's kind of weird. How does it get away with that? Somehow it gets away with that. What's that? I don't have a good answer for that. I have an intuitive idea, but I don't know how to express it at the moment. I will think about it some more. I don't know the answer off the top of my head.
Good try. Is sine negative?
So check it out. Can you see the green circle on there?
Yeah, around.
So would you buy that the red thing takes up half the area inside the circle?
Yes. I could say, yeah, I would agree.
It's pretty darn close to half of it.
Because you could like,
That's kind of cool. So let me see. I want to steal that into my notebook. That's a pretty graph, isn't it? Oh, I told you guys we would do a polar butterfly. I forgot about that.
So this wasn't the butterfly?
No. I totally forgot about that. So this is kind of neat. It just jumps out at me here that if we were to cut this petal in half, that this area right here is equal to this area over here. They have to be the same, according to our calculation. It's kind of wild. All right, shall we go for arc length? Let's go for arc length. Okay, so let's see. Now normally, arc length from Calc 2 is the integral from x equals some starting number a to b, 1 plus dy dx squared dx. And we came up with a parametric version of that which was the integral as t goes from some number question mark to question mark question mark, and that one was the square root of dx dt squared plus dy dt squared dt. Now we need the polar version. What could we use to come up with the polar version? You guys know the answer to this. What have we been using to relate rectangular stuff to polar stuff? Zach? Yeah, y equals r sine theta and x equals r cosine theta. Yeah. So then now we know what dy dx, dy d theta is. So I'm not ready for equals. Dy d theta is equal to, oh, this is the tough part. I'm going to call it r prime for short, times the sine of theta plus r times the cosine of theta. Similarly, dx d theta is going to be equal to r prime cosine theta minus r sine theta. Then what are we going to do? Right? Those are the same things we use to talk about slope. Oops, I missed my r here. There's supposed to be an r there. R sine theta. We need to then take these guys. Now I'm using a theta instead of a t, so I could put thetas here. We need to take these guys and we need to drop them in. Now that's some fun algebra, but I'll let you guys do that later. A whole bunch of shit cancels when you do that. And it's fun to do, actually. It's just a lot of writing. What you end up with in the end for polar arc length is the integral as theta goes from alpha to beta, whatever you decide those are, square root of r squared plus dr d theta squared. D theta. So this particular parameterization just sinks right down. All the sines and cosines disappear. What do you think makes them disappear? Any thoughts? Yeah, sine squared plus cosine squared equals 1. And that's going to pop up all over the place because you are squaring these guys. Actually, you're foiling them out. Right? And tons of stuff cancels. It's amazing. All that stuff cancels. All right. So if you guys are bored tonight, do that. Cancel all that stuff out. Or if you need like some stress relief, I always found this stuff to be great stress relief. Is your phone okay there? You look distraught. Put it away and do some math with us. Come on. Thank you. All right, so now we're ready to find the arc length. We know that r here is equal to the sine of 2 theta. We know that dr d theta is equal to twice the cosine of 2 theta, and so we need that squared. So that's going to be 4 times the cosine squared of 2 theta. So that means my integral, if we go with what we did before, theta goes from 0 to 2 pi, square root of the sine squared of 2 theta plus 4 cosine squared of 2 theta. Now, arc length problems are especially troublesome because there often is not a fundamental antiderivative. Let's toy with it for a second to see if we can find one, and if we can't, we'll try Wolfram alpha. All right, let me see. What can we do with this? Well, I know that sine squared of an angle plus cosine squared of an angle is 1, but the problem there is I have 4 cosine squareds. I could break one of them off. With me? So if I do that, then I could write the inside as I'd have a sine squared plus cosine squared. That would be a 1, but I'd have 3 cosine squared still hanging out. Does that make my life any easier? Not really, because what I'd really like to do is be able to cancel that square root somehow.
Well, you take the square root of 1.
No, you can't split the square root on a sum. Yeah, I can't split the square root on a sum. So we're still trapped inside the square root there. So we have to be able to write the whole inside as a perfect square.
So do we have to use the complete square?
We could try completing the square on it.
Oh, I don't think that's the right answer. Never mind.
I didn't even think about that. That's a great idea. Let's see if that might work. I have no idea.
Yeah, but that wasn't what you were thinking.
I know it wasn't.
Good idea.
I was just thinking that we're not going to be able to do this, and I'd try a few algebraic tricks and then whip out Wolfram alpha. But you came up with an idea I didn't think of. So let's do it. So we have, I'm going to rewrite it as 3 cosine squared of 2 theta plus 1. So I'm just going to call cosine squared of 2 theta, no, I'm going to call cosine of 2 theta 1. So I'm just going to do a little substitution. Let's let x equal cosine of 2 theta. So then that means this is really 3. Oh, it's not going to work.
Okay.
But let's try it anyway. That gives me 3x squared plus 1. Okay. Now completing the squared means I want to rewrite it as 3x squared some middle term plus 1. To find the middle term, you got to have a 1x squared out front, and I have a 3. So I have to factor that 3 out. So that's going to give me x squared blank plus 1/3. Oh shit, no, there's no middle term, which means I can't complete the square. Crap. Darn, it was a good idea though. Wolfram alpha, because I have no other ideas about how to reduce this. All the trig identities I know are not going to clean up 1 plus 3 cosine squared of 2 theta. So, Wolfram alpha this sucker. Am I the only one that has access to Wolfram alpha at the moment? Okay, Wolfram alpha. So what I want to do is I want to integrate the square root of, and I think I'll go back to my original, oh no, I'll just do this one. 1 plus 3 cosine of 2, I'm going to call it x. Square is on the outside. And Wolfram alpha is, ooh, it gives me E, where E is an elliptic integral of the second kind.
That sounds like
Elliptic integrals are very powerful mathematical integrals, but most of them have no fundamental antiderivative. So basically they're just reiterating, this is a very special integral. It has a name, but it has no fundamental antiderivative. So the best we can do is do numerical approximation of it. So let's try that. So now we're going to try to integrate this thing with respect to x, as x goes from 0 to 2 pi. Let's see if Wolfram alpha understands that. It should. Probably should blow up the screen. Yes, it understood it.
like it's about this.
Yeah, so they're saying it's 8 times the elliptic integral of the second kind of 3/4. Elliptic integral, they're very special integrals in math, and to the best of my knowledge, elliptic integrals have no fundamental antiderivative, but they're very important to many fields of study, so they were given a name. Interestingly, elliptic integrals also come up in number theory, studying prime numbers, which is kind of wild. You were working with prime numbers the other day. Yeah, so all kinds of crazy math revolves back to prime numbers, which is interesting. Connectedness of everything. So it's about 9.68845. That's the best we can do. Do you think it's the case here that is there any other way to do this, do you think?
I mean, I'm sure that there is, and someone will eventually figure it out.
Maybe, maybe not, right? So yeah, so there are other things we could do. We could try to find some kind of Taylor series for that, which looks a pretty. It's graphing this as a rectangular function, which has no relation to the function we're looking at. Yeah, so this graph is pretty much meaningless, except the area under this curve happens to be the same as the length of my arc. Yeah. Okay, let's see if 9.68ish seems reasonable. Let's look at the picture here. Uh-oh. You need some napkins or something? So what is the arc length of the green circle? 2 pi.
2 pi.
2 pi is about 6.28ish, yeah. And so do you believe that this is about 30% more arc length than the green circle? So like if we were to take this as a green thing as a piece of string, if we were try to wrap that green string around, it would end right about here. It wouldn't make it all the way to the origin. Does that make sense?
Yeah.
So what I'm saying is cut this right here, and if that was a piece of string or a wire, then pull it down to be tight around that pedal.
Okay, I thought you were, I got you.
And it looks to me that the green thing is not quite as long as that red length in there, is what it looks like. And that's what our numbers are telling us. 6.28 for the green one, 9.68 for the red one, for the arc length. Okay. This is a really important thing in calculus, and I don't know if this point got across in Calc 2, that arc length is very complicated, right? Where's the rest of my arc length formulas? Yeah, this formula, or this formula. And the chance that for some arbitrary function that the square root of all this crap is going to simplify to such a place that you can actually come up with a antiderivative for it is unlikely.
Will you have one, will they be ones that do work or ones that don't work? Or are they just gonna
Unless I say use Wolfram alpha, you may use Wolfram alpha, then the ones I give you will work. Yeah. But if you just randomly pick a polar function like this one right here, the chance that it's actually going to come out nice is slim to none. And that's just the way it is. Yeah. What I did in Wolfram Alpha, let's get back here, let me blow that up, is I said to integrate that function for x as x goes from 0 to 2 pi. So I just, kind of like on the calculator, they do a similar thing. What's your integrand, what's your variable, what's your starting point, what's your ending point? That's a pretty common notation. Yeah, so even on my phone app, I can type that in and it'll do it. It won't show the same stuff as the computer app, but it'll come up with an answer for me. So I will make the final part take home, and there may be a problem like this on the take home where you have to integrate numerically because it's impossible to integrate with shortcuts that we know of. The file's going to have part take home, yeah. Why? Well, here's my problem. At this level, there's some stuff I need you to just show me off the top of your head. But some of these problems are so long and complex, you need to play with it for a day and look at it the next day and see if it makes sense. Or you hit a dead end and you try it again later.
That makes sense.
Right. If I assign 3 hard problems, that could take you 3 hours of sitting down time. Right?
Easily.
Yeah. So with courses like this, part take-home exams really make sense to me because some of the problems, you just can't sit down in an hour or an hour and a half and bang out a few of them.
I'll be graduated. I actually will have time.
All right, cool. All right, that's enough. We're done with chapter 11.
Whoa. Really?
Yeah, that's it. except for the arc length. That was new. Yeah.
That was great learning for me.
Yeah. Okay. There's a recording from last class that repeats this first three things we did: how to graph. And then I started writing the take-home and the final, so I will get that to you by the next class, or maybe post it before then if I have a good day tomorrow.
Are you making a review?
We'll review a little bit on Thursday. We're going to do a little 3D graphing stuff on Tuesday. So we're going to do a little bit of chapter 12. The final is on Tuesday at 1. Does that sound right? Yeah, a week after next. Let me look it up.
Before I graduated, I think I cried. Yeah, you did. Couldn't handle it. Too much.
Calendars.
I think it's
Yeah, it should be. 12 o'clock Tuesday. Thursday is, Tuesday at 1 o'clock. We'll have this room from 1 to 3. Yep, so kind of like the last test, against yourself. It'll be the final exam will be part take home, part in class. About half of the final will encompass the parametric polar stuff. About half of it will be series, Taylor series, power series. And I don't think I'm going to put any of the 3D calculus stuff on there. I think we're just going to play with it for a day and a half. But I'm pretty sure I'm not going to put it on the test. That's it.
awesome.
We're done for today.